this video, I'm going to demonstrate a tricky inflection point question from the IB Math SL exam. It says it's a calculator question, calculator allowed, but then it's asking us for exact coordinates. So that's our clue that we're trying to not use the calculator, because if the answer's like got a pi in it, calculator's going to give us a decimal version, and we won't get full credit when it's asking for an exact answer. So we're looking for the inflection point on the graph of the function y equals sine x plus cosine x. For inflection points, we want to be thinking about the second derivative equal to 0. So we'll take our function y equals sine x plus cosine x and try to get its second derivative. Even if you don't have a plan for the overall question, anything you are able to do successfully on the way to the answer is going to get you some partial credit points. So if at least you know you're supposed to be getting the second derivative, then go there. So the derivative of sine x is cosine x. The derivative of cosine x is minus sine x. That was a nice one because I can just go term by term because of the plus sign in between. If it was multiplication, I'd have to use product rule. It would be much more complicated. So this is actually a pretty easy function to get the second derivative of. Here we are. And we need to set it equal to 0. And the solutions to the equation that we're about to write, those are going to be the x-coordinates of the possible inflection points on this function. Now, the original function, sine x plus cosine x, it's going to look somehow like a wave. And you could graph it on the calculator if you wanted to see it, but it doesn't really help us here. It's just in case you wanted a visual. That red dot, that's the kind of thing we're looking for here. The coordinates of an inflection point on a wave would be where the graph goes from being concave up to concave down. And we only care about solutions on the interval 0 to 4. That's because the wave is infinitely long, so there's going to be a whole bunch of inflection points, but they only care about any inflection point on the interval 0 to 4. And if you're thinking about what x is here, if it's inside of a cosine, right, x is an angle. And anytime we have trig in a calculus question, those angles must be given in radians, which is how we have an interval like 0 to 4 instead of, 0 to 180 or something. So those are going to be radian-sized angles. And if we get our answer, we're going to have to give it in radians. So if we're still trying to do this without a calculator, and you're solving a trig equation, and you've got sines and cosines in it, you might be thinking about trying to use an identity so you can combine them, trying to use factoring so you can use your algebraic skills to solve without the calculator. I can at least factor out a -1. And then I can divide both sides by -1. And then I get a little bit stuck because I don't have an identity that I can use for sine and cosine unless they're squared, and here they're not. So there's no way I'm going to be able to add this sine and this cosine together. And there's no way that moving one of them across the equal sign really helps me either. So this is when I have to have this lightning bolt of genius, where I'm realizing that if I'm adding two numbers together and they equal 0, then those two numbers must be the opposites of each other. For example, like this could be 2 and this could be -2. Except for that we know cosine and sine can't be greater than 1 or less than -1. But that's just an example of, if you think about these two numbers having to be opposites of each other, you might realize you're looking for an angle for x where the sine and the cosine are the same, but one's negative and the other one's positive. So I'm thinking this quadrant, sine is positive, cosine is negative, and I'm thinking this quadrant where cosine is positive and sine is negative. And moreover, specifically, I know it's got to be a 45-degree angle because that's where the sine and cosine have the same value. In a 45-degree angle, the sine is root 2 over 2, and the cosine is root 2 over 2. So I'm thinking that this angle, and I shouldn't say 45 degrees, I should be saying pi over 4. This angle, which is a pi over 4, but in the second quadrant, is going to be 3 pi over 4. And this angle is going to be almost the whole way around the circle, less one last little 45-degree angle, so a 7 pi over 4. So these are two possible angles where the sine and the cosine would be opposite values to each other, right? Because if you're thinking about a 45, 45, 90 here, you might label the sides 1 and -1 and root 2. And indeed, the sine of that angle and the cosine of that angle would have a sum of 0. 3 pi over 4, this value, is 3 approximately times 3.14. It's about 9 divided by 4. That does come out in the 0 to 4 region. So I'm going to give that as one of my answers, that x could be 3 pi over 4. I'm going to check the other answer and see if it's also in the 0 to 4. So 7 times 3.14, that's about 21 divided by 4. That's more than 5. So that's not even a viable answer. So this is it. This is the only x value between 0 and 4. where the sine and the cosine would have opposite values and then therefore add up to 0. So that's the x-coordinate. It also wants the y-coordinate because it did say exact coordinates, meaning once you found x, plug it back in to find y. And we always plug back into the original function to find a y value. Well, when we plug that into the original function, we can see it's the sine of 3 pi over 4 plus the cosine of 3 pi over 4, which we know is 0. That's how we actually got here. So y is going to be 0. So now we have our coordinates. And then it asks us to verify analytically that it's actually an inflection point. And for that, we like to do a second derivative sign chart. So f double prime of x, or y double prime, that's what I've been using here, y prime, where 3 pi over 4 is the point we're proposing is an inflection point. We want to test something on the left and something on the right in the second derivative. That's why this is called a second derivative sign chart. This was the second derivative, to see if indeed the sign is changing. So if you plug in something like 1 pi over 4 and a 5 pi over 4 into this second derivative, you'll see that before 3 pi over 4, so let's say we're plugging in pi over 4, plug it into the second derivative. You're doing the sine of 45, or the sine of pi over 4, which is root 2 over 2, but it's negative, minus root 2 over 2. So a negative minus further, this comes out negative. If you plug in something greater than 3 pi over 4, like let's say 5 pi over 4, then we have a negative negative, which is positive. And the cosine of 5 pi over 4 is also negative. So it's a positive plus a positive. And since the sign is indeed changing of the second derivative, that means that your inflection point, that your point actually is an inflection point, because the concavity has changed from concave down. That's what a negative second derivative tells us. Concave down. Sorry for the bad spelling. And a positive second derivative tells us that over here, the function is concave up. And so since concavity is changing, we have verified that indeed this is an inflection point.